If you follow tech news at all, you've probably seen the breathless headlines, right? The ones promising that quantum computers are about to instantly solve all of humanity's problems by next Tuesday. Well, let's take a breath and actually systematically break down these massive expectations. In this explainer, we're going to look at the actual data and the latest peer-reviewed breakthroughs to separate what is real from what is pure PR hype, and figure out where this industry is really heading. We've got a really fascinating lineup today. We're going to start with hype versus quantum reality, look at where we are now, and dive into developing error correction. After that, we'll map out navigating the quantum future, tackle the quantum laptop question, and finally, discuss access over universal ownership. Let's get right into it. Section 1. Hype versus quantum reality. To start us off, we need to quickly ground ourselves in the physics. Now, you already know that qubits just don't play by classical rules. By harnessing quantum behaviors, specifically superposition and entanglement, they can exist in multiple states and interact completely simultaneously. I mean, it sounds like science fiction, but this is the literal operating system of nature, and engineers are actively trying to tame it right now. And that brings us to the core thesis of this entire explainer. While the underlying math is genuinely starting to work at scale, the physical reality of building these machines is incredibly demanding. Look, the industry is solving the reliability problem surprisingly fast. But making these machines small and accessible, that is a completely separate and honestly a much harder problem. Moving to Section 2, where we are now. To really understand that physical hurdle, we have to look at the hardware. We are currently in what researchers call the NISQ era. That stands for Noisy Intermediate Scale Quantum. Think of it as the Wild West of hardware. There is literally no single dominant architecture yet, which is a massive sign that this field is still in its early, highly experimental days. For example, IBM has been iterating through their Eagle and Heron superconducting chips, which, just like Google's setups, require these massive absolute zero cooling systems. But then contrast that with D-Wave. They just announced a major breakthrough in scalable on-chip control for their qubits, vastly reducing all that insane wiring complexity. And then on the totally opposite end of the spectrum, Stanford University recently demonstrated a nanoscale optical device using twisted light to entangle photons at room temperature. No extreme cooling required. The sheer diversity here tells us the winning hardware design is still completely up for grabs. All right, Section 3, Developing Error Correction. Because regardless of the architecture, the absolute biggest obstacle right now is noise and error. Qubits are incredibly fragile. A tiny interaction with their environment, and poof, they lose their quantum state in a fraction of a second. But we just hit a monumental engineering tipping point. Google unveiled their new Willow chip, and the metrics are just staggering. Willow completed a standard benchmark calculation in under 5 minutes. To do that exact same calculation on Frontier, which is one of the world's fastest classical supercomputers, it would take an estimated 10 septillion years. That vastly exceeds the age of the universe. But you know what's crazy? Raw speed isn't actually Willow's most important breakthrough. The real game changer is that Willow achieved what physicists call below-threshold error correction. Historically, the problem was that if you added more physical qubits to a system, you just introduced more noise and made things worse. But Willow proved that by scaling up the number of qubits, they actually cut the logical error rate in half with each step. So for the very first time, quantum computing is actually shifting from a theoretical physics experiment into a viable, scalable engineering discipline. But, and this is a massive but, we absolutely must remain critical. Because for every genuine milestone like Willow, there are dozens of corporate press releases promising the moon. A recent University of Pittsburgh study in the journal Science is the perfect reality check here. The researchers tried to replicate a bunch of highly publicized so-called smoking gun breakthroughs. And guess what? They found that these flashy signals could often be explained away by much simpler classical physics when they rigorously ran the data. It's a stark reminder that in the quantum space, rigorous peer replication always has to trump PR hype. Section 4. Navigating the quantum future. Let's look ahead and see how this builds into an actionable timeline, keeping that healthy skepticism in mind, of course. IBM's updated technology atlas lays out a pretty aggressive path. They're targeting their Nighthawk processor with 360 qubits for 2025, a modular, error-corrected system called Starling by 2027, and aiming for a fully fault-tolerant system, BlueJ, capable of running 1 billion gates on 2,000 qubits by 2029. By 2033, they project full-scale utility. It sounds amazing, right? But here is the critical analysis. Historical data from this highly experimental industry tells us that roadmap dates almost always slip. So it's safer to view this as an optimistic trajectory rather than a guaranteed calendar. Still, when these roadmaps actually are realized, the hybrid quantum classical workflows they enable are going to utterly transform massive industries. We're talking precise molecular simulations for drug discovery, designing vastly more efficient EV batteries, and optimizing complex aerodynamics, like Boeing is doing with their Quick project. And crucially, there is the urgent need for post-quantum cryptography migration. Why? Because bad actors are literally harvesting encrypted data today, just holding on to it, with the intention of decrypting it the second these fault-tolerant quantum machines come online.
Which brings us to Section 5, the quantum laptop question.
This is a very practical question about how you and I are actually going to use this immense power. Will we all have a quantum processor sitting inside our personal laptops or smartphones in the next 10 years? I mean, it's a super fun sci-fi concept. The dream of a personal quantum chip seamlessly accelerating your daily tasks is great. But the engineering reality check is that miniaturization is a brutal physics problem. Think about those superconducting chips from Google and IBM we mentioned. They require specialized dilution refrigerators just to keep them at absolute zero. And even if we perfect room temperature optical chips, you still have massive error correction overhead, insane control lines, and complex laser arrays. Honestly, achieving the raw performance gains is proving to be much easier than shrinking the required physical infrastructure. You really have to think of it like the massive mainframes of the mid-20th century. The sheer physical footprint of quantum architecture prohibits it from being a personal device anytime soon. Those early room-filling classical computers didn't just magically jump into people's pockets overnight. They became shared utilities first. And that is exactly the path quantum computing is taking. And that sets us up perfectly for Section 6, access over universal ownership. So if it's not going to be sitting on your desk, how do you harness it? The undeniable middle path here is the Quantum as a Service model, or QAS. Platforms like AWS Braket, Microsoft Azure Quantum, and the IBM Quantum Network are entirely operational right now. And we're also seeing the rise of hybrid quantum-inspired platforms like BQ-Fi, which deliver massive engineering optimization right now on existing GPU infrastructure, acting as a bridge until the pure quantum hardware fully matures. In this model, your routine computations run locally on your laptop, but the incredibly complex mathematical bottlenecks, those get pushed to a quantum processor in the cloud. So the data paints a crystal clear picture. Quantum's future is universal access as a shared cloud utility, definitely not universal ownership of personal hardware. Deloitte actually predicted that even by 2030, quantum power will primarily reach consumers through the cloud. And we're seeing that happen today. Organizations are already using their existing high-performance computing infrastructures to interface with cloud-based quantum processors. The utility model isn't just a future prediction, it's the standard right now. Which leaves us with a fascinating, and let's be honest, slightly daunting reality to consider. As error rates drop and reliability scales up in these massive centralized data centers, the literal power to simulate nature itself is going to be heavily consolidated. So I'll leave you with this to ponder. If the greatest computational leap in human history is exclusively accessed through the cloud, whoever manages those gateways will ultimately dictate the pace of human discovery. What does that mean for the rest of us? Thanks for joining me on this explainer, and I'll catch you next time.